Now let us discuss maximum power transfer theorem for DC circuit especially. So in general, if there is a network containing resistances and sources, then when we are going to connect the load in that particular network, then maximum power will get transferred if the Thevenin's equivalent resistance RTH is equal to the load resistance. So basic theorem states that load resistance RL connected to a source or a network receives maximum power when its ohmic value RL is equal to internal resistance RS of the source or Thevenin's equivalent resistance RTH of the network. Now let us assume the variable load resistance here we will consider, and RL is connected to DC network as shown in this figure. The DC network across the terminal X5 can be represented by Thevenin's equivalent circuit. So containing voltage source VTH in series with resistance RTH. So this will look like this Thevenin's equivalent resistance. And now if we apply KVL around the loop, then VTH is equal to I into RTH plus RL. So I is equal to VTH divided by RTH plus RL. The power loss in the load resistance RL will be given by PL is equal to I square RL, or it will be V into I. Now, if RL is equal to 0, then PL is equal to 0. And if RL equal to infinity, then I is equal to 0. And then also PL is equal to 0. So this is very, very important kind of a assumption or fact, we can say. Not assumption, rather it is a fact. Like when load resistance is going to be very small, at that time the voltage drop across that load resistance will be very small, and therefore it will not able to produce the sufficient power, and that's why power will be very small, that is approximated to 0. And when load resistance is very high, then it will not able to allow a significant current. The current will be very small, and therefore again that current will not able to produce the appropriate power. So that's why when RL is equal to 0, then also PL is equal to 0. And if RL is going to tend to infinity, then PL is not going to become infinity, but PL is also going to tend to 0 because current is going to drop. So thus these two extreme cases of RL causes 0 power delivered to load. However, for value of RL other than 0 and infinity, some power delivered to the load we are going to get. And putting value of I into this equation, we can write PL equation as I square RL, which is VTH by RTH plus RL bracket square into RL. In this equation, the variable quantity is RL. For power PL to be maximum with respect to RL at some value, if its derivative with respect to load resistance is taken, and if this first derivative is going to become 0, then maximum power will get transferred. So condition for maximum power transfer is the first derivative with respect to which this PL is going to vary, that must be 0. So this is very, very important assumption in this whole derivation. So ddRL of, now here for PL we will write VTH I square RL. So I square corresponds to VTH square divided by RTH plus RL bracket square into RL, and that is equal to 0. So here VTH is constant, just bring it outside. ddRL of RL upon RTH plus RL bracket square. This RL upon RTH plus RL bracket square equal to 0. Now VTH square will keep as it is. This is derivative of U by V. So V into derivative of U minus U into derivative of V. So derivative of U is ddRL of RL will be 1. So that's why here it is 1 minus RL RTH plus RL whole bracket square. Its derivative will be RTH square plus 2 RTH into RL plus RL square. So RTH square and 2 RTH into RL. So that part and RL square. So here it will become 2 RL its derivative, and 1 is RTH into 2 into RTH into RL. So from that 2 is taken common. So into bracket 2 and into RL. So this is U, that is U into derivative of this denominator. So RTH square derivative is 0 because it's a constant. 2 RTH RL derivative will be dd of that 2 RL, that is dd of RL only 2, and the last term 2RL. So that's why this is the term written equal to 0, and denominator is V square. So that is RTH plus RL bracket square whole square. So now since we want to make it this 0, so this denominator will get 0. Whatever is VTH is multiplied, that will also get 0, and the term remaining will be RTH plus RL whole bracket square minus RL into 2 into bracket RTH plus RL, that the whole numerator term, that is equal to 0. So little bit split, RTH plus RL, RTH plus RL minus 2RL, RTH plus RL is equal to 0, and therefore RTH plus RL minus 2RL is equal to 0, and RTH minus RL is equal to 0. Therefore RL is equal to RTH. So condition for maximum power transfer is equal to PL max, that is equal to VTH square divided by 4RL, because in this PL expression we have RH plus RL. So instead of RH, if we write, it is an RL and whole, that square term. So resultant will be VTH square divided by 4RL. So instead of a network, if a practical voltage source V in series with its internal resistance RS supplies power to a load resistance RL, then the maximum power will be transferred when RL is equal to RS. A current source I in parallel with its internal resistance RS will supply maximum power to a load resistance RL if RL is equal to RS. So in both cases, this is a true condition. In short, source supplies maximum power to a load if load resistance is equal to source resistance.